August 17, 2017. 8:41 and 10 seconds a.m. For the first time in human history, we simultaneously saw and heard cosmic violence. At that instant, four gravitational wave detectors around the world vibrated in unison. LIGO in the United States, Virgo in Italy. The signal lasted 100 seconds, frequency rising from 30 Hz to 1000 Hz, like the universe screaming, pitch getting higher and higher, more and more urgent. Then it stopped abruptly. 2 seconds later, a gamma ray burst reached Earth. The Fermi Space Telescope captured it, lasting 2 seconds, brightness equivalent to 1000 supernovae exploding simultaneously. 11 hours later, 70 observatories worldwide pointed at the same coordinates. Southern celestial sphere. Direction of Hydra constellation. 130 million light-years from Earth. What they saw rewrote physics textbooks. It was two neutron stars colliding. Not black holes, not ordinary stars, but corpses of dead stars, the densest form of matter. A teaspoon weighs 1 billion tons. These two neutron stars, each only 20 kilometers in diameter, smaller than Beijing's Fifth Ring Road, but each with 1.5 times the Sun's mass. They orbited each other for 100 million years, losing energy with each orbit, radiating away as gravitational waves. The orbit grew smaller and smaller, speed faster and faster. On the final day, they rotated 1,000 times per second, surface velocity reaching 30% of light speed. In the final second, they were only 100 kilometers apart, gravity pulled each into ellipsoids, surfaces began tearing, matter ejecting from equators, forming two spiral arms, rotating like galaxies. In the final 0.01 seconds, two 20-kilometer iron balls collided head-on at 100,000 kilometers per hour. The energy released in that 0.01 seconds equaled the Sun's total output over 10 billion years. Not 100 years, not 1 million years, but 10 billion years compressed into 0.01 seconds. Temperature instantly reached 10 trillion degrees. At this temperature, iron decomposes into protons and neutrons fuse into heavier elements. Gold, platinum, uranium. The shockwave from the impact expanded outward at light speed, sweeping through surrounding interstellar gas, igniting a supernova explosion with brightness 100 billion times that of the Sun. But that's not even the most astonishing part. Wait. There's something more shocking. Scientists calculated the composition of ejected matter. 16,000 Earth masses of material were thrown out. Among it, 10 Earth masses were gold, 100 Earth masses were platinum, 300 Earth masses were uranium. Let's make these numbers concrete. All the gold currently on Earth totals about 200,000 tons. If melted into a cube, the edge would only be 21 meters, fitting inside an Olympic swimming pool. That collision produced the equivalent of 60 trillion tons of gold in 0.01 seconds, 300 million times all of Earth's gold. This gold flew out at 10% of light speed, temperature 10 billion degrees, glowing blue-white. Over the following weeks, this debris cloud slowly cooled, changing from blue to red, then dimming. Astronomers gave this phenomenon a name, kilonova. 1,000 times brighter than a nova, 1,000 times dimmer than a supernova, right in between. And the gold atoms in that debris cloud would drift through the universe for billions of years, then some would come to Earth. 4.5 billion years ago, the solar system was still a cloud of gas and dust, collapsing into the Sun and planets. That dust mixed with material from hundreds of supernovae, and also mixed with material from at least one neutron star collision. After Earth formed, heavy elements sank to the core, light elements floated to the surface, but some gold still remained in the crust. Billions of years later, through tectonic movement, volcanic eruptions, erosion, and sedimentation, this gold was concentrated into ore veins. Then humans appeared, dug out this gold, smelted it, forged it, made it into rings, necklaces, coins. The gold ring on your finger, every single gold atom was born in a neutron star collision. maybe 5 billion years ago, maybe 10 billion years ago, in some distant galaxy, two dead stars collided at 30% of light speed. That collision released energy exceeding an entire galaxy's brightness in 0.01 seconds. The ejected gold atoms flew through the universe for billions of years, through interstellar space, through molecular clouds, through the birth and death of stars. Eventually, they landed in the forming solar system, got trapped in Earth's crust, waited 4 billion years, then were dug out by humans. Now it's on your hand. But this is still happening. The 2017 collision wasn't the only one. Scientists estimate that in the Milky Way, a neutron star collision occurs every 100,000 years. Right now, somewhere we can't see, two neutron stars might be spiraling toward each other. Perhaps in Andromeda Galaxy, 2.5 million light-years away, two neutron stars have been orbiting for 50 million years. Now entering their final stage, rotating 100 times per second. In 10 years they'll collide, but we'll have to wait 2.5 million years to see that collision's light. Perhaps in the Virgo cluster, 54 million light-years away, a collision is happening right now. The ejected gold will be found, smelted, and used 54 million years from now by some civilization we cannot imagine. And the gravitational waves from that collision are traveling toward us at light speed, still needing 54 million years to arrive. By then, humanity might no longer exist, but the gravitational waves will pass through Earth's former location and continue forward forever. Before 2017, scientists only theorized that heavy elements came from neutron star collisions. After August 17, 2017, we saw it with our own eyes. Spectroscopic analysis confirmed that debris cloud contained gold, platinum, rare earth elements, uranium, thorium. All elements heavier than iron on Earth come entirely from neutron star collisions or from certain special supernovae. Nuclear fusion inside stars can only produce up to iron. Iron is the most stable element. Further fusion would absorb energy rather than release it, so stars stop at iron. To create elements heavier than iron requires extreme conditions, temperatures above 10 billion degrees, pressure 10 to the 30th power times Earth's atmospheric pressure, neutron density of 10 to the 38th power per cubic centimeter. Only two places have these conditions, neutron star collisions, or the cores of supermassive stars exploding. And neutron star collisions are the primary source of gold production. Scientists calculated that 80% of the universe's gold comes from neutron star collisions, only 20% from supernovae. In other words, every gold atom on you has an 80% probability of being born from two dead stars tearing each other apart. The 2017 discovery opened a new era, multi-messenger astronomy. Gravitational waves tell us two supermassive objects are colliding. Gamma-ray bursts tell us the collision produced high-energy radiation. Visible light tells us a kilonova eruption occurred. Spectroscopic analysis tells us the ejecta contains gold and platinum. From 2017 until now, we've detected gravitational waves from 5 more neutron star collisions, but all too distant for optical telescopes to see. Scientists are waiting for the next one, within 300 million light-years. Close enough for detailed observation. The James Webb Space Telescope is ready, Hubble is on standby, 70 ground-based telescopes form an observation network. Once gravitational wave detectors sound the alarm, all telescopes will point to those coordinates within 30 seconds. We'll see what it looked like 1 second before collision, the flash at the moment of impact, the kilonova's evolution process, real-time spectroscopy of gold formation. Maybe in 2025, maybe in 2030, maybe tomorrow. Somewhere, two neutron stars are completing their final orbits, preparing to collide. And the gold ejected when they collide will be captured by some planet billions of years later, discovered by some civilization, crafted into some piece of jewelry, worn on some being's hand, just like the ring on your hand now. Think about this. Every single atom in your body has its own story. The hydrogen in your body was born in the first 3 minutes after the Big Bang, 13.8 billion years ago, in the 10 billion degree primordial fireball. The carbon in your body was born in some red giant's core, 5 billion years ago, in a 100 million degree fusion furnace. The iron in your body was born in some supernova's explosion, 6 billion years ago. That star spent 10 million years making iron, then exploded in 1 second, blasting iron across the universe. And if you're wearing a gold ring, those gold atoms were born in a neutron star collision, maybe 8 billion years ago, maybe 12 billion years ago, in some galaxy we'll never see. That collision lasted 0.01 seconds, released energy exceeding the sun's 10 billion year output, ejected 10 Earth masses of gold. Then those gold atoms flew through the universe for billions of years, through thousands of light years of void, witnessing countless star births and deaths. Eventually they came to the solar system, got trapped in Earth, waited 4 billion years. Until one day humans dug them out, smelted them, forged them. Now it's on your hand. You wear it while scrolling your phone, drinking coffee, riding the subway, doing what you do every day. But that ring on your hand witnessed the universe's most violent moment. Every atom is a souvenir from 2 dead stars colliding. So next time you look at the gold ring on your hand, remember it came from billions of light years away, born in the universe's most spectacular fireworks, traveled billions of years just to be on your finger at this moment. And right now, somewhere we can't see, 2 other neutron stars are completing their final spiral, preparing to collide, preparing to create more gold. Preparing to send them across the universe. Maybe billions of years from now, that gold will be discovered by some civilization. Maybe that civilization will, like us, wear it, then look up at the stars, wondering where it came from.